Shapes of atomic orbitals. When a planet moves around the Sun, you can plot a definite path for it, which is called an orbit. A simple view of the atom looks similar, and you may have pictured the electrons as orbiting around the nucleus. The truth is different, and electrons in fact inhabit regions of space known as orbitals. The quantum mechanical treatment of electrons in atoms gives a clear picture of the energy levels associated with every atomic orbital, which can be defined by a set of 4 quantum numbers. Solutions of the Schrödinger equation correspond to waves rather than to particles, and at least in principle, all electromagnetic waves extend throughout all space. The location of an electron can be described in either of 2 equivalent ways using the quantum mechanical results. If the electron is visualized as a real, very small object moving very rapidly, then the space it occupies can be described in terms of the probability of finding the electron at a given point or within a given space at any instant. The values of all 4 quantum numbers influence the location of an electron, or in the terminology just introduced, the distribution of electron density in space or the shape of an orbital, but the effects of the 4 different numbers are not the same. The principal quantum number n affects primarily the size of the orbital and has a lesser influence on its shape. The subshell quantum number L affects primarily the shape of the orbital. The magnetic quantum number m affects primarily the orientation of the orbital in 3-dimensional space. The spin quantum number s has little effect upon the location of the orbitals of an isolated atom, but does have an influence on orbital interactions when the orbitals of different atoms impinge upon each other. Orbitals with subshell quantum number L is equal to 0 are called s orbitals. All s orbitals are spherical in shape and have spherical symmetry. This means that the wave function will depend only on the distance from the nucleus and not on the direction. In any atom, the size of the s orbital increases as the principal quantum number of the orbital increases, but the geometry remains spherical. The electron density also tends to extend further. Other orbitals behave in the same way as the principal quantum numbers of the orbitals increase. Orbitals with subshell quantum number L is equal to 1 are called p orbitals. Since the magnetic quantum number m, L, can be -1, 0 or +1 when the value of the subshell quantum number L is 1, p orbitals come in sets of 3. In each set, one of the orbitals is aligned along each of the 3 mutually perpendicular axes of the atom. These axes are traditionally designated X, Y, and Z. The 3 2p orbitals are correspondingly designated 2px, 2py and 2pz. The p orbitals, either as a set or individually, do not have spherical symmetry, and so a simple plot of radial probability density cannot be made for them. Orbitals with subshell quantum number L is equal to 2 are called d orbitals, since ML can be -2, -1, 0, +1 or +2. When L is 2, d orbitals come in sets of 5. The d orbitals and the more complex f orbitals are usually visualized in three-dimensional representations, even if these have to be shown on a two-dimensional page. Orbitals with subshell quantum number L is equal to 3 are called f orbitals. These orbitals are found only in the lanthanide and actinide elements. Since ML can be -3, -2, -1, 0, +1, +2 or +3, when L has the value 3, f orbitals come in sets of 7. The f orbitals are rarely of direct chemical interest because they tend to be buried deep within the electronic cloud of an atom, but they do play a major role in the spectroscopy of the lanthanides and actinides.